But most people actually, let's go on though and say what can we do in the interim times before we really know for sure. Most people are pretty confident in the Standard Model. It's never been wrong. Okay? So we're pretty sure that this Higgs field is filling all of space, and it does exist. So we're pretty sure, and we've had some little clue there. So let's suppose it's right. Let's suppose the Higgs boson is discovered, and we know that there is this omnipresent Higgs field. There's a very serious problem with this idea, okay? Because it's been known for 50 years that if you have this vacuum energy, that's what the Higgs boson is. It fills empty space and it has energy, okay? It has a very weird effect on the universe, okay? Einstein's theory of general relativity shows that the universe has to either contract or expand, and it's been measured that the universe is expanding. Okay? If you take, and it's the cause of the expansion is the matter in it. If you take the universe and fill it with stars and galaxies and atoms and material, dark matter, anything, it will expand, and the gravity of those things in it will cause the expansion to slow down. Okay? And by measuring the speed at which it's slowing down, you can actually measure how much stuff is in the universe. People have been trying to do this for 50 years. Okay? If there's enough material, in fact, the universe will eventually stop expanding and start to contract and go back to a big crunch. So this theory, this Big Bang theory, based on Einstein's theory of general relativity, is really well accepted and well tested. It explains many things. It explains the cosmic microwave background. It explains the number of helium atoms in the universe. It gives a very promising theory of structure formation and galaxy formation. Explains the expansion of the universe. It's basically the only game in town. So we're really, in the same way with the Standard Model of particle physics, we're stuck with this model, standard cosmology. But it's been known for a long time that vacuum energy has a very different effect on the expansion of the universe. If you take a box, or not a box, but a region of the universe, and it's full of atoms, say, and expands, the number of atoms will stay the same. And so the expansion rate will go down. The expansion rate is driven by the amount of material inside a region. Now, if you take that same region and fill it with vacuum, which of course it automatically is, and now you expand, you've got more vacuum. If every cubic centimeter has vacuum energy, you've got more energy. The expansion rate will go even more. Now, it really takes solving the theory of general relativity and a lot of math to show this, but it's an absolutely inescapable conclusion of general relativity that if you have vacuum energy, the universe will undergo a runaway, accelerating, exponential expansion. Okay? Now, the Standard Model says, in fact, that the Higgs field, it fills up the universe. And it even tells how much it is. The Higgs field in 1 cubic centimeter is more than 1 trillion tons. That's how much it is. 1 trillion tons per cc. Okay? Can you feel that? Well, as I said, you actually do feel it because your hand is able to move slowly. It's what gives you the mass. But if you plug that number into Einstein's equations, you'll find in less than a nanosecond, the universe should have expanded to 1 billion times its current size. Something is terribly, terribly, terribly wrong with this theory. Okay? Where's the problem? Okay? Well, in fact, there's a very easy but very ugly theoretical solution to this. Okay? And it's one of the major unsolved problems in particle physics. Here's the solution. Okay, the Higgs field fills all of space with more than 1 trillion tons per cc. Let's take another field, an unknown ad hoc field that's never been invented. Just for this purpose we'll invent it. And it fills all of space but contributes minus trillions of tons per cc and cancels it out. Now, in regular life, we can't have negative energy. Everything we have is positive energy. But in quantum field theory, the vacuum is allowed, perfectly consistent mathematically, is allowed to have negative energy. So there's nothing mathematically or theoretically wrong with having this minus vacuum energy. Except it's very weird that we have to take some ad hoc field and cancel out this stuff. And it's even worse than this because lots of other fields in particle physics, the quark fields, for example, also contribute vacuum energy. And that has to be canceled out too. Okay? So this is called the cosmological constant problem. Because the vacuum energy, cosmological constant is another name for the vacuum energy. The cosmological constant was introduced by Einstein. He later called it his latest blunder. His biggest blunder, it actually is here now, and we'll see why in just a second. So what's interesting is that that this cancellation has to happen, and no one knows how it happens. In fact, some of the biggest names in particle theory, Ed Witten and Steven Weinberg, have said that the most important unsolved problem in particle physics is the cosmological constant problem. How to arrange this cancellation. Okay. Now, there was a huge new wrinkle to this, happened a couple years ago, by people playing around with telescopes like this. Some of my friends at Berkeley went out and said, well, let's test this hypothesis. Let's see whether the universe is expanding. How is it expanding? Is it speeding up or slowing down? Is the universe filled with ordinary material, in which case the expansion should be slowing down, or is it filled with vacuum energy, in which case it should be speeding up? And you can do this because looking out in space is looking back in time. If you see a galaxy 1,000,000 light years away, you're seeing the light took 1,000,000 years to get to you. You're seeing it as it was 1,000,000 years ago. So if you go out and find galaxies billions of light years away, you can see what the universe was doing 1,000,000,000 years ago or more, right? So we use the Keck telescope, use the Hubble Space Telescope to do this, and what they do is they look at supernovas. Okay? So they find these distant galaxies. That's a supernova there. It's an exploding star, and they're wonderful. They're all the same brightness, and by measuring them very carefully, you can see exactly how far away they are and how fast they're moving away from you. So you can actually measure the expansion rate as a function of time. There's another supernova there. There's another supernova. And these are some nearby supernova remnants. The blast wave from the exploded star looks like this after a few thousand years. But for the few weeks that a supernova happens, that one star becomes as bright as the 100 million or 100 billion stars in this galaxy. I don't know how big that galaxy is. That's why I had to say that. Okay. So what did they find? Well, they found, in fact, that in the past, the universe was expanding slower. That means today it's expanding faster. That means the expansion is speeding up, which means that vacuum energy is driving the expansion. Any kind of ordinary material would have slowed the universe down as it expanded, but it's speeding up. So we are actually going through this exponential expansion that I described. We're actually in it right now. Okay, this was a shock to the scientific world, even though it was a theoretical possibility for 50 years. People didn't expect it. But it was called the Science Story of the Year by Science Magazine in 1999. So it's an amazing discovery. And one nice thing about it is that you can say, okay, I said the Higgs field was more than 1 trillion tons per cc. These guys can measure how much is the vacuum energy. And they can do it. It's about 10 to the minus 29 grams per cc. That's about 1 proton mass per cubic foot. So this makes the cosmological constant problem even more acute. You have to take this trillions of tons, cancel it off, and leave 10 to the minus 29 grams in each cubic centimeter. This is a very precise cancellation, and nobody has a clue on what mechanism is causing that. Okay. So this stuff, even though it doesn't seem like much, 1 proton per cubic foot, there's a lot of space out there. And in fact, if you add up the stuff in the vacuum, it's 10 times more than all the atoms and everything known. Okay? It's twice as much as the mysterious dark matter. So this vacuum energy, the energy of empty space, we now know, is the dominant substance in the universe. It's driving the universe. It's determining our fate. Okay? So there we are. Well, where are we going to go from here? Okay? How are we going to make progress? We don't understand this. Well, particle experimentalists can maybe find the Higgs and tell us if this is right or not. And there are other theoretical ideas such as supersymmetry that really help in this cancellation. Okay? Astronomers can measure the expansion rate more accurately and tell us a very important thing: is this vacuum energy changing with time or not? The cosmological constant is a constant with time. The vacuum energy could change. If they find it changing with time, it will be a great clue on what kind of quantum field is responsible. We don't know what quantum field is responsible for the expansion of the universe now. But what we really need here is a theory. We need a theory that'll predict what's going on here in the vacuum and tell us that. If you think about what kind of theory could do this, it turns out there's really only one that people have thought of. And this is a brand new theory, not that new, but theoretically new, superstring theory. Okay? Superstring theory is the first consistent theory we have of quantum gravity. It's a very speculative theory at this point, but it holds a lot of promise. Now, you may know that Einstein wasted the last decades of his life trying to find a unified field theory. He wanted to make electromagnetism and gravity all part of one unified theory. And he failed miserably, and it's clear now why he failed miserably. He didn't know about the Standard Model. He didn't know about gauge symmetries. He didn't know about nuclear forces or quarks or any of the things you would need to put together a unified field theory. But his dream of a unified field theory stayed on, and finally, maybe 10 or 15 years ago, the superstring theory came along, and that is the first candidate we have had. It's a very beautiful and elegant theory, but unlike the theories I've talked about before, which are well tested by experiment, superstring theory has no experimental test. So it's speculative. Okay? So I'm shifting into a much more speculative place right now. Okay?